This is Module 2, Lecture 5-2, the next portion of Lecture 5 on Research Design and Data Management. And in this portion of the lecture, we are going to talk about causal association. So up until now, we have talked about ruling out spurious association and chance. Now we consider evidence that could establish a causal association. Of course, as part of chance, although we haven't lectured on it specifically, is the correlation along our spectrum from 0% to 100% association. The 100% now, of course, under consideration is causal association. So there are several criteria, and we'll discuss each of these separately: strength, consistency, biological plausibility, temporal correctness, and specificity. Now, it's not required to satisfy all of these criteria, but obviously the more criteria satisfied under one particular investigation, or over time, as we will see, the better the condition for establishing the causal association. So the first criterion is strength, also referred to as strength of relationship, or SOR, between the test factor and the outcome. So our independent variable, the test factor, and the outcome, the dependent variable. And this is measured by magnitude of difference, or effect size. Remember, we saw this in our general discussion on the test statistic, the difference between the means of the two groups in the case of a t-test. So the effect size is very important. Effect size, if you have more than two groups, of course, is the effect size between any two particular comparisons in the test used ultimately to evaluate statistically significant difference possibilities between any of the groups when you have greater than two groups. So as the effect size increases, the strength of a relationship increases. So we've seen this in our discussions all throughout, as we've talked about bar graphs, line graphs, comparing 2 points on two different line graphs, or two different bars on two different bar graphs. So this is no stranger to us. So the effect size is expressed as difference between groups. It can be expressed as proportions, means that we most commonly find ourselves dealing with. This conveys the magnitude, or ratios, which conveys the causal importance. So sometimes it's important to look at your data in all of these fashions to see which may represent an effect size that demonstrates the greatest strength. Next, consistency. So the more consistent the finding in the greater number of studies between test factor and outcome, then the greater the association is causal. And obviously this is where I mentioned over time originally. It's best when different investigators in different populations or samples produce the same results. Next is biological plausibility. So the results must fit into the theoretical framework of the existing knowledge, and we'll consider this again in another illustrative type of representation of the theoretical framework as we had seen earlier. So in this illustration, in figure 12.1, the schema of a research report, we can evaluate what we just described for the biological plausibility. So basically this is our theoretical framework with reference to our other model. Excuse me. And this is the realm of the data down below, and obviously the subproblems and the hypotheses are in between, and of course the execution of the experiments, collection and the analysis of data is in this area here. Let's take a look at the peripheral areas first. Up here on the upper left, the peripheral areas are the discussion of the related literature, classic and contemporary. And then on the right, the peripheral areas are delimitations, definitions, assumptions, importance of the study, and the organization of the remainder of the study. So these are inherent aspects of considering the theoretical framework as we recall. So back to our um, feel for this biological plausibility, fitting our results from the data back into the theoretical framework. So here we see the area of subproblem 1 with hypothesis 1. In other words, this is an identified gap in the theoretical framework. Ask a question, generate an hypothesis, design experiments to test the hypothesis, collect the data, evaluate the data, interpret the data, and determine if it supports the hypothesis. If the facts support the hypothesis, in our case, we think of the experimental results. If the data support the hypothesis, then of course it's possible to fit that hypothesis into the gap within the theoretical framework. Here under the subproblem 2, gap 2, hypothesis was put forth, the experiment was performed, and the facts did not support the hypothesis. Then here we see we're bypassing the hypothesis. We come back to the area of subproblem 2 and begin this approach to re-identify the gap, reconsider, ask new questions, come up with new answers, and generate new hypotheses that hopefully can be tested and supported by the data. And of course, hypothesis 3 here is being shown as another subproblem area in which the data did support the hypothesis, so we're filling 2 out of 3 gaps in this example. Again, under biological plausibility, it's a good idea to demonstrate a dose-response relationship. In other words, the association between the degree of exposure and the size of the change in the outcome, the effect size, are very important. Biological systems should demonstrate dose-response relationships. Not all will necessarily, but we would expect it in nearly every case. So simply because it doesn't would not prevent us from establishing a biological plausibility. The biological system under investigation would have to have all the properties to expect a reasonable dose-response relationship. It doesn't always happen, but the majority of the times you should be able to establish it with a few doses at least. So we recall a positive dose-response relationship. As X increases, the value of Y increases, or a negative a negative relationship. As X increases, Y decreases. So a positive slope and a negative slope, respectively. Next, temporal correctness. So the test factor must precede the outcome. So this is quite obvious, but there's other important characteristics of temporal correctness. We have to keep in mind that most of our biological studies are freeze frame. We terminate experiments to collect our data at different time points using separate samples. Or even if we are able to sample over time, as we'll see, this becomes a repeated measures type of a study, where from the same samples you collect data at different time points. And of course, this is in effect establishing a temporal correctness. So many events in biology happen over a relatively short period of time. One example that comes to mind is if you're measuring levels of transcription factors. When do you measure them? Or even intracellular chemical signals, maybe that become phosphorylated, and you're using a complex biological system, especially like behavior of an animal. When do you measure, and really what does that mean within the temporal sequence of events that you are ultimately trying to understand based upon the gap that you pointed out? So temporal correctness has a much more complex level of evaluation and creativity in experimental design than what is reflected by this very obvious statement: the test factor must precede the outcome. If you're getting a change in your dependent variable before you've made any change in your independent variable, obviously you can't have a causal association, or it'd be extremely highly unlikely that you would. And then specificity. So the test factor must be related only to one outcome. And we recall that when we talked about bias, of course, we're at this point assuming that we ruled out spurious association. So um, with controlling bias and confound and all the possible sources of variance or variability in the measurement of our outcome, our dependent variable or outcome measure, we're trying to control everything so that the independent variable, the test factor, is the only one being modified and therefore should, in a well-controlled experiment, should establish the specificity. Now there are other approaches, and using drugs that act at receptors, like using an agonist or testing the endogenous chemical signal, you can block the receptor and demonstrate that you don't get the change in the outcome when you modify the test factor. In other words, the independent variable no longer produces the change in the dependent variable because you have blocked the mechanism through which your test factor acts to bring about the outcome. So this is a very important aspect of studies to establish a causal association. Some type of intervention within the biological system where you have a known and reliable intervention factor that can eliminate the biological effect of the test factor and thereby show that the outcome is completely dependent upon this mechanism of action of the test factor. So specificity becomes extremely important, in my mind at least, as one of the primary criteria for establishing a causal association. Now, in the last few slides, we will discuss the questions for hypothesis testing. And in this definition of hypothesis testing, I am taking the scientific perspective of the theoretical model, the gaps, questions, answers that are hypotheses, and so on and so forth. So the scientific hypothesis testing, not merely the statistical hypothesis testing. So you identify the study design after you have identified the gap in your hypothesis, of course. What are the groups to be compared? On what basis are the groups being compared? And what is the study design? So after reaching this point, achieving these three aspects of the study design, go on to rule out bias. So what bias might be present in the design of the study? For a cohort study in humans and clinical trials, were all the subjects taken from the same pool? So are you sampling appropriately? In assessing the outcome, were the observers blinded to the risk factors status of the subjects? Again, this might seem foreign if we don't work with humans, but we do ask ourselves, is the experimenter at the bench blinded to all aspects of the ongoing experiment at the bench at that moment? So if you do know what chemical you are adding as part of your experiment, specifically related to the test factor and its relationship to the outcome, then you introduce a bias, as we know. Was the information on the outcome obtained in a similar manner for all groups? So the inter-assay variation and the intra-assay variation is extremely important in this context. Was there different attrition from the study groups? This is the dropout. Were there any loss of data points? Were they justified? And do any of them need to be included throughout? And of course, randomization is extremely important. Continuing with ruling out bias, for the case control studies, were all the subjects taken from the same population? This is familiar to us. Were the controls chosen from an appropriate group? So are you assigning your treated samples randomly from the same source as you are for the controls. Did you use all the feasible control groups possible and reasonable? Were deceased cases included? I guess that's not really important for us. But if your culture or your animal dies, what do you do with that? That's related to dropout. Were observers blinded to the disease status and so on and so forth? Was information for the risk factor obtained in a similar manner for cases and controls? So are you collecting data through the same means for your treated and your control groups? In other words, are you doing only your treated groups on one day and your controls on another day? Or are you running some controls and some treated simultaneously, such that you can't account for the differences between your control and your treated groups based upon inter-assay variation, let's say, or some type of bias from day to day or test to test? Rule out confounding is next. Were the groups similar at baseline by demographics or clinical characteristics? So obviously your sampling is extremely important again. If the groups were not similar, was the possibility of confounding controlled for in the study design by restriction, stratification, or matching? We discussed all these. Or in the analysis by stratification or regression analysis. So we remind ourselves that we can deal with confound before and after the collection of the data, and it must be strictly organized with specific criteria that must be satisfied to exclude before and or after. Then to rule out chance, was a statistically significant difference found between the groups? If the results were not significant, was the sample size adequate to detect the difference? So here's the estimate of sample size and power analysis showing its importance. Could bias or confounding be masking real differences between groups? So go back to check on that spurious association. Did you indeed rule it out? If the results were significant, did the researchers account for multiple statistical tests in interpreting the p-value, and did they perform appropriate multiple comparisons procedures? So we'll talk about the statistics in forthcoming lectures and help to understand this information. Then establish a causal association. As we just saw, was there evidence of a causal association according to the following criteria: the strength, consistency, biological plausibility, and temporal correctness and specificity. This approach is, of course, extremely valuable and an obligation in designing our experiments, and all the way to reporting the experimental results, but also this sequence of analyses of any experiment are important in evaluating a research report, an article, if you have to do so for a journal club or whenever you're reading a research article for whatever utility. So this completes our discussion of establishing